Hello and welcome to another video. In this video we're going to be doing the third problem of the biweekly contest, which is minimum number of operations to make x and y equal. And in this problem you're given x and y, and in one operation you can do one of the following. You can divide x by 11 if it's a multiple of 11, divide by 5 if it's a multiple of 5, decrement by 1 or increment by 1, and return the minimum number of operations to make x and y equal. So in this first one, what you want to do is you want to do 26 minus 1, which is one operation. Then you will get 25, then you will divide by 5 twice, so you get 3 operations total. In the second example, what you want to do is you want to add 1 to get 55, which is one operation. Then you can divide by 11 to get 5. Then you can divide by 5 to get 1, and then you can increment by 1. And that's the least you can do. And then in the last one, you just want to increment 5 times. And the constraints are important for this problem to know like what kind of things you can do. So they are relatively small, so you can't have like an n-squared solution, but you can have like a linear time or something like that. So let's talk about like what we can do here. Basically, we have a bunch of choices we can do, and there's kind of like two main ways to solve this problem, and I'll briefly talk about either one. So whenever we have all these choices and our decision depends on previous choices, we always want to look for DP, right? Because that's like that's usually like one of the most common ones. You have a bunch of choices, you're trying to get some result. Can you make this work? And so what choices do we have? Well, we have these choices, right? So here they are. And let's think about how we could do this in DP, and then we'll talk about another way. So in DP, we need to figure out like we need to figure out some states, some base case and a recursive case, and quickly take the constraint and figure out, will this pass given the constraint? You know, is there like not an infinite loop and so on? Okay, so let's talk about the states. So for the state, really all we need to do here is, it's kind of obvious, right? We just need to figure out like what our value is, right? Like we'll have an x value. Our target never changes. Like we're always trying to make x equals y. So the y will always stay the same, but we just have like an x value that we currently have, which is fine because that's only 10 to the fourth, so that should be fine. Okay, what about a base case? And this one's a little bit trickier. So obviously when value equals y, we can return 0, but is there anything else that we can like optimize? And there actually is. So notice that this is a decrement, this is a decrement, and this is a decrement, and we only have one increment operation. So if we have like x equals 25 and y equals whatever that's bigger, like 100, we only have one way to increment this, right? And so we know right away that basically the only way to do this is just keep incrementing by 1. Right? So here the answer would be 75 operations where you just increment by 1 because we only have one increment operation and it can only increment by 1. So that's another base case, is x or value is less than y, return y minus x, right? Because you can only basically do a increment. Now this part is kind of tricky, the recursive. So the problem would just we can't just like increment forever because we'll have an infinite loop, right? Like let's say our number is like or not an infinite loop, but an infinite recursion. Let's say our x is like 25 and our y is like 5. Well, yeah, obviously you could divide by 5, but you don't know like that's the best. So you can't just like do all 4 of these. You can't just do like an increment and a decrement and divide, because you will only actually cache your results when it's done. So what's going to happen is you're going to recurse to like 26, then you're going to recurse to 25, recurse to 26, recurse to 25, and so on. And you will never actually cache anything because like you don't have like an endpoint. And even if your endpoint was like, if it's divisible by 5, never do an increment because that's bad. Okay, well, what if your number was like 26 instead? Then you would like go to, or let's say not 26, let's say it was like 27. Then you would like, okay, it's not divisible by 5, it's not divisible by 11, maybe I need an increase, maybe I need a decrease. So I'll go like 27, then I'll go to 28, then I'll go to 29, then like maybe I'll go back down to 28, 27, and so on, right? So you have an infinite loop, an infinite recursive stack if you do something like that. So notice, like in this example, you will sometimes need to increment, right? It's not always, you can't always take the greedy thing of like, if y is less than x, let me just decrement until I can do some division. Because here, notice that you are supposed to increment. But there is a greedy thing we can do, let's say we have 54 and we're trying to get 2. We're never going to want to like increment forever, right? We're never going to want to increment forever. And ideally, we don't want to increment at all. We want to figure out what values to increment to so we don't have this infinite loop of like incrementing to 55, decrementing to 54, blah, 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 right? Ideally, we want to figure out like what value do we increment to and then do a divide right away, right? So if we have 54, yeah, sure, we might increment to 55 and then do a divide by like 11 or 5 to get some number. So let's say we get 54 and we increment to 55. And then we do a divide by 5, we'll get 11. And let's say we try that again with divide by 11. We get a 5. But is there a better way to get something, like, is there a point to ever incrementing farther than the first number we can divide by 5 and the first number we can divide by 11? Well, not really, right? Like, let's say, like, if we have 55 or 54, we can go to 55 and then turn that into 2 things, right? Let's actually use, instead of this, let's use a better number because 55 is divisible by both 11 and 5. So let's do something else. Let's do like 47 or something. So 47, we can either increment to 50 and then we can get it down to a 10, which is 2 operations, or we can increment it up to 55 and then get it down to 11, right? By dividing by 11. But we're never gonna like want to increment, and then also let's figure out how long this takes, right? This is 8 operations, this is 3. We're never gonna want to like increment past these 2, because if we wanted to get like 12 or something, or 11 or any of these numbers, it's always going to be cheaper to just do the division and then do the increment afterwards, right? So if we wanted to go from 47 to 12, let's say, or like 13 or any of those numbers, like let's say we want just a number bigger than these. If we want to go to 12, it's always going to be faster to just go to 50, divide, and then add like 1 or 2, as opposed to go to 50 and instead of stopping at 50, go to like 60 and then divide by 5 to get 12, right? Because it's always cheaper to, so we can write this down. It's always cheaper to divide, then add some small number, then increment by 5 or 11 more, right? Because basically, instead of going from 11 to 12, by incrementing, like if you increment to go from 11 to 12 by dividing by 5, you would have to add another 5. But if you want to go from 11 to 12, you can divide first and then add like 1 or 2. So we can figure out that when we have a number, we never want to increment past first number we can divide by 5 and 11. So we have to do this for both of them, right? So for 47, we're going to say like, okay, we have 47. We're trying to get, let's say, 3 or whatever. We're never going to want to increment past 50 and divide by 5, right? Because it's just always cheaper to do something else. And we're never going to want to increment past 55 and divide by 11. Like these will be the optimal values to increment to, and we can calculate this. And so that's kind of what our recursive stuff is going to look like. So let's go back to our actual cases here. So let's write down some things. So first, obviously, we can just do a decrement. Now, you can optimize a decrement as well, but the constraints are small enough to where that doesn't matter. Like, you can just subtract 1. If your constraints were bigger, you could optimize a decrement as well, where you're never going to... And I think there's, like, a hard problem like this, where the constraints are, like, 10 to the 9th or 10 to the 12th. And it's kind of the same idea, where you don't really want to decrement by 1. You want to decrement to a number that you can divide by 5 or 11. And you just want to make sure that when you do decrement to those, that y isn't in that range. Like, let's say you had 53 and you decremented to 50. You wanted to make sure that like y wasn't like 51 or something. But in our case, we can just do a simple subtract by 1 because the constraints are small enough. So let's look at our recursive cases. So 1, we can decrement by 1. By 1, and this is 1 operation. 2, and this is going to break down into 2 subcases. So 1, divide by 5, if possible. Right? So if possible to divide by 5, we can divide by 5. And then we can say, if not, right? Actually, I think you can do this in like a bunch of different ways. Yeah, so because our decrement, we'll always try decrement. Yeah, okay. So what we can do here is we can decrement, and then we could divide by 5 if possible, which is just one operation. And then we can say if not, like let's say our number is 54 again. We can't divide this by 5, like going back to this first example. We can't divide this by 5. But what we can do is figure out what to increment to divide by 5. Then divide by 5. And so the number of like steps that takes depends on the number. For example, 54, 54 to make it go to 55 would take one operation. And then the one more for divide by 5, let's say our number is like 51. To go to 55 would take 4 operations and so on. And this is you can easily figure this out. Just do like a mod 5, figure out like how much more do I need. So if I mod 5, I have 1, I need 5, that means I need 4 operations, something like that, right? And I'll show you this in the code to make it a lot clearer. So basically figure out like what to increment, and we're never gonna want to increment to like 60 or something, right? Because like I said, it's always cheaper to divide and then like add 1 or 2 or whatever we need. So that's gonna be number 2. Then we have number 3 is going to be very similar, which is just same thing except for 11. So we can just write that down. So yeah. Okay, so same as B, but for 11, right? So if our number, once again, was like, let's say 63 or something, we'd say like, is this divisible by 11? No, it's not. Well, what do we want to increment to? We want to increment to 66 because that's 3 operations and the divide is 1 more. We're never going to want to increment to like 77 or something and divide by 11 because 77 divided by 11 will give us 7, but it takes so long to get here, right? It's like 20 or something, not 20, but like 14, where we can just increment here, divide by 11, get 6, and then add 1. And that's always going to be cheaper than incrementing past. So that's the main thing you have to recognize. And then I think, so we have, let's see, we have the divide, we have the decrement, and we have, yeah, like I said, we're combining the increment with the divides to not have like an infinite loop. And so that's how you do that for DP, and then you just basically return the minimum. Now there is another way to do this, and it's a breadth first search. And the reason this works is because if you look at it, if you just try all the moves, and your numbers are in this range, that means like the most it will ever take you is like, I think it's going to be a lot less than this in reality, right? Like, I don't see how this can happen. So in reality, it's going to be like significantly less than this. Maybe it's hard to calculate. Maybe it's like logarithmic or something, right? Because if your number is like, let's say 10,000 or something, and y is like 1, like you can just keep dividing by 5 or keep dividing by 11. So the number of moves is going to be like a log of this. But even if it wasn't log, even if the number of moves was 10 to the 4th, basically what you do is, let's say we start at 54, and we're trying to get to 2. So we can literally just breadth first search and keep track of the moves. So we can just say like 54 is 0 moves. And then for 54, where can we go? We can go to 55, which will be 1 move. We can go to subtract 1, 53, which will be 1 move. And then we can't go anywhere else, right? So because this is not divisible by 5 or 11. And you just keep doing this, and you have a visited set to make sure you never revisit the same number. So then the most states you'll ever have is like 10,000, right? Which is like going to easily pass. So this is also O of n. And basically, it's a lot simpler logic-wise because you don't have to worry about like incrementing and having an infinite loop. Because every time you increment, yeah, you will keep incrementing, but you're just going to get to your answer like before your increment number is big enough. So your increment number will be like, and you could add logic to handle the increment as well, but you don't really need to do that. So you could say like when my number is something, instead of incrementing, I could figure out like how many moves this takes. But because you're doing a breadth first search, ideally you just want to take 1 move at a time. Now the other alternative is you can use a heap, and then you can, instead of only doing 1 move, you can do multiple moves, and then you can always just take the like least number of moves available in your heap. That will also work. So if you have like 54, we can kind of do our DP strategy where we can decrement, which is 53 and 1. Or instead of incrementing, we can just do the increment and divide in 1 operation. So we could say like, okay, to divide by 5, basically what's going to happen here is it's going to be 1 operation to make it go to 55, and then another one to divide by 5. So we'll actually have 11 here, and that'll take 2 operations. And we can divide by 11 as well, which will give us a 5 with 2 operations. And then you keep putting these into the heap, and you just keep taking the smallest thing until you get your answer. So that also works. And let's go over the code. And I think this is like a lot less complicated because with DP, you do have to have these like avoid infinite cases. But in the BFS, it's like really straightforward. You can just use all of your like super basic stuff. And because the constraints are so small, it'll pass anyway. Because like I said, even though technically you are incrementing to numbers that are never going to be an answer because you're only making one move at a time and the maximum number of moves is like 10,000. But actually, it's going to be a lot less than that in reality, right? Because like I said, you're going to get there a lot faster. Probably going to be like log 10,000, which is like 20 or 30 or something. So in reality, this is going to finish really fast, right? Like you can actually try this with like whatever numbers you want, and I think it'll be pretty fast. Okay, so let's look at both of our things. So here is our DP solution that I coded, and then I was coding the BFS afterwards. So here's DP. So like I said, if our value is less than y, there's only one thing we can do. We just have to increment it up to y because we only have one increment operation. Then we have our cache operation. Then we have our decrement operation, which, like I said, you can't optimize this instead of decrementing by 1. And in some problems that is needed, but in this one, the constraints are small enough where it doesn't matter. Then we just check, can we divide our number by 5? If we can, let's do that state, one operation and divide by 5. And if we can't figure out what number to increment it up to, increment it up to that and then divide by 5. And the number of operations is pretty straightforward. How many operations did it take you to increment? And then the 1 for division. So that's why it's 6 minus this mod remainder thing. Same thing for 11, literally the same code. Cache it, return it. So this does work. Now we can look at the BFS, which is a lot more straightforward. So you basically just have a deck, you have a visited set, you append x and 0, and then you literally just check, am I at y? If I'm at y, return the number of moves. If I can divide by 5 and I haven't visited that yet, let's add that. If I can divide by 11 and I haven't visited that yet, let's do that. If I can obviously always add 1, but if that number isn't in visited, let's do that. And if the minus is not a visited, let's do that as well. And whatever one gives me the answer first is the answer. So like I said, you can do this with a BFS, you can do this with Jigstras and not make one move at a time. You can make whatever you want with a heap. That would also work. Yeah, and I am curious. So if we do actually run a test case with like some big numbers, let's say x is like, let's take a look at, so 10 to the 4th. So let's say x is like 10 to the 4th is 10,000. So we can do like 9, 8, something, 3 or something. And y is like, I don't know, something like this. Like I expect this to be like 20. So let's see. Yeah, so you're never gonna get. That's why this works with the BFS really fast, because your number of moves is always really small. It's like logarithmic. Because like you're always gonna be able to divide at some point. So like no matter what you pick here, this is never gonna be very big. And yeah, so yeah, and this is like pretty fast. I think they're about the same runtime for DP and for the BFS. But like I said, if these constraints were bigger, then I would go more towards DP. Because adding 1 is not efficient, right? Or you could optimize, like I said, you could optimize your BFS into a heap, and then that would also make it more efficient. But yeah, adding 1 move is not like great. I think it'll still actually work. Yeah, I think it will work still, because basically you will just like never use that operation. So I think the BFS would still be fine even if the constraints were bigger. But yeah, I would probably optimize the DP a little bit. Instead of like just subtracting 1, I would kind of do the same thing I was saying, right? Like for example, if your number is 10,000, you're never gonna like want to go to like this and this and this and so on. You're always gonna want to divide instead of subtracting if you can. So you can kind of do the same thing. You can just like subtract down to a number you can divide and then divide. As long as your y value isn't like in that range or something. So yeah, so not too bad. You can, like I said, you can code this up with this, BFS, Jigstras, whatever you want. Yeah, so let's go through. I think, yeah, the runtime is all the same. So this is O of n because we have basically, like this is going to be like the biggest value you can have. And then you're never going to increment it by that much. So you just look at like, since x is 10 to the 4th, that's what it's going to be like. That's going to be the runtime, 10 to the 4th. Because if you have 10 to the 4th, you will increment it by like 5 or 11, but that doesn't really matter. And like I said, in reality, I think this is more like logarithmic. Um, hmm. Well, actually, no, I don't actually. Sorry, I don't think it's logarithmic. I think it'll still be a linear because like in the way at least I have it, you're still always doing this, so your cache size will still be pretty big. So for example, if we and we can actually test this. So if this is this, if we print, so if we print cache dot length or length cache or something, I think this will still be like pretty big. So if we call dpx and then print the length of the cache, yeah, so the cache is still like a lot of items. So this was linear time. Okay. Yeah, so this is linear time, and these if things don't matter because this is the constant time. And then for the space, it's O(m) as well. So yeah, the most important thing to take out of this is this like increment trick that you never want to like keep incrementing. You always want to increment to a value you can divide because you can prove that incrementing past that is never going to be better than just dividing and then adding later on. Yeah, so that's going to be all for this one, and then I'll do the last one pretty soon. So hopefully you guys like this one, and if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.